Hello guys, let's solve number of squareful arrays today. So in this question we are given an array nums and we need to return the number of permutations of nums that are squareful. So what is a squareful array? So it's an array where the sum of every pair of adjacent elements is a perfect square. So given this example 117.8, uh, the answer is 2 because we have only two permutations which are squareful, which is 1, 8, 17. So this is squareful because uh, 1 plus 8 is 9, which is a perfect square, and 8 plus 17 is 25, which is again a perfect square. So we see how the sum of adjacent pairs are all square numbers. Similarly for this permutation. And note that they are also asking us to count permutations only those that are unique. So in this example, nums is 222. So even though there are probably going to be like 6 permutations that are totally generated, but they are all going to be just 222. So we return just one. We just need to count the unique permutations that are squareful, right? And with respect to the constraints, we can see that the length of the array is just 12. Yeah. So let's see how to solve this problem. Yeah, all right. So let's see what is the absolute brute force method to solve this problem. So whenever we are dealing with permutations, most likely the solution is going to involve recursion. So let's just sort of recursively generate all possible permutations, and for each permutation, let's check if the array is squareful. If yes, we count it, right? So this is probably the absolute most brute force method that we can do for this problem. So let's see how to do that. Yeah, so let's start coding this solution. Uh, let's first define our recursive function that is actually going to generate all the permutations. So I'm going to call it permute, and index represents from where the recursion actually starts. So when index is equal to the length of the array, that means that one complete permutation has been generated, and we can go ahead and add it to our result set. And here we're going to do the check if the array is actually squareful. We need to implement this method later, and in that case we're going to add it to our set. So let me define a set. So I'm defining a set because I want to add only unique combinations. I don't want any duplicate permutations. So I'm going to say result.add, and in order to make it hashable, you need to convert it to a tuple. You can't add an array to a set directly, right? And in that case, I'm going to just return, right? And now we can do the loop followed by the recursion. So we need to so this is a pretty standard code to generate permutations. So if you guys are not aware of this, I would strongly suggest you to try to understand this first, because only if you understand this you will actually understand the optimization as well, right? So we're gonna iterate from index till the last element of the array. So the first thing that we'll be doing is doing a swap of in index, and once we do a swap, we can now do the recursion. So commute array, and we're gonna start recursing from the next index, right? And that is gonna generate a tree of recursion. And once you're done with the tree of recursion, we need to swap it back. So this is the backtracking step basically. We basically need to swap it back, right? And yeah, that is pretty much it for this code. So we'll let's kickstart recursion, and then finally all we need to do is return the length of result, right? And we just need to implement this method right now. So we call it is squareful. The input is going to be an array, and so what is a squareful array? Every pair of adjacent elements needs to be a perfect square, right? So I just need to do for I in the range length of array I plus array of I plus 1. That's why I'm treating only till minus 1 because I'll be checking at every point. I'll be checking I and the I plus 1th value. I'll be adding it and I'll be checking it if it's a perfect square or not. If it's not a perfect square, we can go ahead and return false immediately, right? And if all the adjacent elements are indeed perfect squares, we'll reach this part of the code segment and then we can return true, right? And then one final method that we need to implement right now is to check if a number is a perfect square. So there are probably like many methods to do this. I'm just going to use the math on square root method for this. So I'm going to take the square root of n, square root of num, and then I'm going to subtract it with the int value of the square root of num. And if this is equal to 0, that means that this is indeed a perfect square. So if I have 25 here, 25 square root of 25 is going to be 5.0, and the int value of it is again going to be 5.0, so I get 0. But if it's say 30, the square root of 30 is going to be 5 point something, but minus the int value of that is going to be just 5, so that is going to give you a decimal value which is not equal to 0. So that's how you can pretty easily find if a number is a perfect square or not. So if this is returned true, if this is the case, if not, we can just return false, right? Let me just add some brackets for clarity. Yeah. Cool. This should at least pass the base cases. Let's try this as a 117.8. Yeah, it actually passes. But we know that this is a pretty highly time complex method, and we know that it's probably going to time out. Yeah, so that's what is happening. So now let's further try to understand how exactly this permutation is actually working, and let's see how to optimize it. Yeah, so this is the recursion tree for the given input 117 and 8, and the value for each box. I've also mentioned the index value corresponding to the recursion level, and for each branch I've also mentioned what is the swap operation that's actually happening, right? So let's start here. Index is 0. That means we're going to loop from 0 to 2, and then in the first step we're going to swap just 1 and 1. You get the same array, you reach index equals 1, and then you swap, you fix this, and then you swap 17 and 17, and then you get 117.8, and that is going to be your first permutation, right? So this is the recursion tree that we have right now. But let's try to understand, do you really need all possible recursions? The answer is definitely no, because we have one huge condition saying that every adjacent pair needs to be, the sum of every adjacent pair needs to be a square number, right? So a lot of recursions are actually pointless. So let's see how to actually prune these trees. So at the first level, so that's the key idea is that you will go ahead and recurse only if the array before index is actually squareful, right? So at index equals 0, you definitely have to prune because you don't really have anything to check before 0. So this recursion definitely has to happen. And when you reach here, the next swap that you're doing is actually swapping 17 with 17. And then once you do the swap, the array that you have is 117 and 8, right? Now we can immediately do the check. We can check if the sum of the value at index and the value before it, is it a square number or not? So 1 plus 17 is 18. It is not a square number. So we can immediately stop this recursion. We don't even need to go ahead with this subtree of the recursion at all. So that is the key idea behind this method. So this is a small example where there's just 3 values. So let's say there are 5 values here, or even 10 values. So completely avoiding this one branch is going to save you thousands of computations. And let's just do one more example. So let's say now we're going to this part of the tree. So in this part, the swap that's happening is 17 and 8. So once you do the swap, the array that you have is 1, 8 and 17. And then you immediately check, is this part of the array squareful? So 1 plus 8 is 9. That is indeed a square number. So this tree, this branch is okay. We need to recurse along this path, right? So so this is the big optimization that we'll be doing to reduce the complexity of this code. And one other small method that we can actually use is so let's say our input array is 1, 1, 1, 17 and 8, right? So we're clearly given that we need only unique permutations. So let's say we are done permuting with the first value, and then we shift I. Let's say index is 0, and then we shift I. We know that recursing down this index is going to generate the same permutations. So what we can do is we can actually skip these values because they're the same value, right? So we can skip these and we can go to the next value that's not same as 1. So notice how we have like a requirement that the array needs to be sorted first, right? So if 1, 1, 1, 17, 8 is the input, we need to first sort it so that we get something like 1, 1, 1, 8, 17. Because the input can actually be even like 1, 8, 1, 1, 17. We need to sort it so that we have all the same numbers together, right? So that we can just skip through the same numbers and start recursing from the next different value. So yeah, these are the 2 optimizations that we'll be doing, and that should be good enough to pass this problem. So let's see how to code it. Yeah, so let's see how to incorporate these optimizations into the current code that we have. So like I said, the first thing that we need to do is actually sort the array, because we need to skip over the duplicates, which means the duplicates need to be together. So let's first sort it, and then moving to the recursion. So this is where we're going to implement our optimization to prune a lot of branches. So do we always recurse? No. When do we recurse? When either index is 0. So for the first value of index, we definitely need to recurse, or if index is greater than 0 and the sum of the adjacent values are a perfect square, right? So that I can just use this function, is perfect square, nums of index plus nums of index plus 1. So I'm checking if index and index minus 1, the sum of that is a perfect square, and only then I'm actually permuting. So you see how a lot of unnecessary permutations are being saved here, right? And the second optimization was the skipping the duplicate values. So for that, what we're going to do is just if nums of I is equal to nums of index, that means we've already recursed for this particular value, so we're just going to say continue. And mind that I will initially take the value of index, so we'll just add that case. If I is greater than index and nums of I is equal to nums of index, then we can continue, right? And the last change is we don't really need this condition anymore, because since we are always making sure we are recursing only if it is squareful, we know that if index actually reaches the length of the array, then the entire array is definitely squareful. So we can remove this condition and directly just add it to our result set, right? So we don't really need this method anymore. And let's see if this works. The base case does work, and yeah, it finally passes. So the time complexity of this code is again going to be exponential. It's going to be something of the order of n factorial. But how the reason why this works is because of these two key optimizations, where we do the recursion only if the array up to index is actually squareful, and the other optimization is skipping over the duplicates. So this is a pretty hard problem, I guess. It's tagged hard as well. There are probably other methods to solve this too, but I thought this is a pretty easy method to understand, right? Alright, thank you for watching.